Hello, and welcome to this webinar on new features in LS-DYNA version R13. R13 is being released right now. We expect the executables to be on our website next week with the documentation to follow shortly after. The policy continues of issuing minor updates to previous major releases. You can see on the screen the current versions of all of the most recent ones. These are the topics to be covered in this presentation. Rather than try to explain every little thing that's been added to R13, we'll just focus on a small number of items in each subject area. You can always find out more information in the release notes if you wish to delve into those. We'll start with isogeometric analysis, since this is quite a big area for development at the moment. Isogeometric analysis started with element shell NURBS patch, but that's now been superseded by the family of keywords beginning with *IGA. And the point of this is that IGA keywords are closer to the way that CAD works, in particular the way the surface geometry is defined. So the LS-DYNA model is working from the same geometry as the CAD. We're not losing geometric accuracy from the meshing. And the new *IGA cards enable better continuity and connectivity of the surfaces. But there is still pre-processing required. You can't just take a CAD model and input it to LS-DYNA. Currently, only ANSYR can create IGA shells, and even ANSYR can't do the solids yet, but they're working on it. LS Prepost reads and displays them, but doesn't create them, and the next version of Primer will do the same, displaying them too. *IGA supports Bezier extractions, which is one of the ways in which CAD can represent geometry. It allows for arbitrary complex topologies to be represented with one patch per part without the need for trimming. Bezier extractions come as solids and shells, and they support contact, spot welds with heat affected zone, element erosion, and so on. A new feature is that surfaces can be joined with edge-to-edge tied contact without needing to split the geometry of this outer blue tube along the join line. And this tied contact couples rotations as well as translations. The way CAD defines geometry, you have control points which are outside the boundaries of the surface. These become nodes in the LS-DYNA model, and features like rigid walls have to know not to treat them as if they were normal structural nodes and not to create any contact forces on them, and that's been done in R13. It's a similar thing with connections, loads, and boundary conditions. There isn't always a node in the place where you want to attach that feature. And so now a keyword's been added enabling you to define such points, for example, around the edge of a hole, onto which you can fix boundary conditions, connections, loads, and so on. So what about spot weld type connections? Well, if you're modeling spot welds with beam or solid elements using mapped spot weld, you'd normally tie those to a shell element mesh with tied contact, and that's done in exactly the same way with IGA shell elements. They tie to the panels through tied contact. The SPR3 constraint is a special case because it doesn't work through tied contact, but it is still mesh independent. It goes looking for the appropriate nodes of the shell mesh automatically, and that now works with IGA elements too. So the advantage of having these mesh independent ways of modeling spot welds is that if the shell element mesh changes, then they automatically stick to the new mesh just as they did to the old mesh, and that works the same with IGA as well. These so-called continuum shells are the IGA equivalent of thick shell elements. Look like a solid, behave like a shell. So in respect of looking like a solid, you can have contact on both faces, and the through thickness stress is being modeled as well. In respect of being like a shell, it's just one element through the thickness, but it can still do bending accurately. Moving on now to material models and elements. So there's a new feature called Matte Add Inelasticity, which enables you to add certain plastic and creep effects to any other material model. It's a little bit like Matte Add Erosion or Matte Add Damage in that it can be applied to any other material. So you might have a material type 24, for example, and you want to add creep to that. So you have your Matte 24 definition, and you also have Matte Add Inelasticity with the same material ID, and that enables you to add a creep function onto that existing material data. So material 123 has had some new functions added to enable it to model plastics better, and specifically so that the elastic stiffness can be made strain rate dependent. There have been some developments in terms of cohesive elements and materials. Certain foam materials can now be applied to cohesive element types, so you can model sandwiches with a thin layer of compressible foam. There's also a feature on control solid. It's an input field called ICOH, which means that when the underlying shell element gets deleted, any cohesive elements attached to it also get deleted, so they're not left flying around free in the model, potentially causing trouble like riderless horses in the Grand National. And that feature can now be applied to Matte 169, which is matte Arup adhesive as well. So that could be a useful way of keeping the model nice and stable. This slide describes a new capability for modelling gaskets, as for example, the gasket interfacing between this exhaust manifold and the engine block. Because gaskets are very thin, but the through thickness direct stress behaviour is important, this is an ideal application for cohesive elements, which is what this material model uses. Here, it's the compression response that we're interested in. The material behaves somewhat like a foam in that it can crush and recover at small to medium strains here, but then at higher strains it locks up. And the user supplies load curves to define the loading and unloading behavior. When spot welds are modeled with, particularly with a single solid element with matte spot weld, if you apply tension to the spot weld, the element naturally wants to shrink laterally, but that's prevented by the constraint from the attached panel. So it will tend to develop tension in the plane of the shells as well as normal to them. That can cause some issues with accuracy and stability. So there's a new feature. You can add the word uniaxial onto the matte spot weld definition, which stops that from happening, and then the transverse stresses are set to 0. And there are a few other enhancements shown on the slide related to defining the failure properties of spot welds related to the properties of the attached panels. Matte bolt beam models a bolted joint with a single beam element, and it includes inputs to model preloads, clearance holes, sliding against friction, and so on. It was available in previous releases, but the new feature here is an option to model the bolt tearing through the sheets, producing an elongated hole. And that means that if you then push the plates back in the other direction, the bolt's got to slide all the way across that longer hole before it picks up force on the other side. And the resistance to tearing through the sheets is given by a user-supplied load curve. With thermal material models that have anisotropy, i.e. different conductivity or other properties in different directions, the methods for defining the local material directions have been brought into line with the structural materials, so the same AOPT settings are now available as they are for the structural materials. There's a new solid element formulation that still gives good results even for really unfavourable element shapes. The next subject area is airbags and safety devices. So there are some enhancements around the modelling of vents for the corpuscular airbag modelling method. Essentially, the definition of these vents is a bit more flexible now, with the same card being used for internal and external vents. When using this feature to model internal vents, the behavior depends on whether you've created chambers within the airbag. So in this case, we have chambers with an internal vent between. In that case, the new option enables, once the vent breaks away, it enables the pressures in the two chambers to come together very quickly and accurately. And there's another use case where chambers have not been defined, and when the vent breaks away, there can be bi-directional flow between the two chambers. And when modeling external vents, there's a new feature enabling the airbag particles to continue to apply forces to the vent cover right until it's flown a certain distance away from the edge of the hole. And this slide shows the input fields needed to invoke that new feature. Here's a new feature for pushing up the bonnet for an active bonnet release for pedestrian protection. The input's a bit like a simple airbag model where the user defines a mass flow curve and the size of the chamber that the gas is flowing into, and LS-DYNA then calculates the pressure to apply at the bottom of the actuator there, which then pushes the bonnet up. Define pressure tube models a pedestrian impact sensor, which is a tube embedded in the front bumper. The signal from the sensor relates to pressure changes in the tube, but it's not just a case of reduction of volume from the impact with the pedestrian, giving an increase of pressure in the tube. The impact occurs quickly, so there's a pressure wave transmission effect along the tube. And this slide is about improvements in modeling the wave transmission. Moving on to connections and contact now. The constrained SPRs have their own way of tying themselves to the sheets in a mesh-independent manner. These now work with solids as well as with shells. Orthotropic friction means different friction factors according to the direction of sliding, and this is of particular relevance to seatbelts. This was available in R12, but the input has been made much easier in R13 because you no longer have to define the fabric directions for the dummy, only for the seatbelt. The so-called mortar contact has a more physically correct way of distributing contact forces between the contacting elements. It's essential in many implicit analyses, but can also be used in explicit and may be especially helpful in models with larger time steps like this one. There have been a number of improvements in this feature, which I won't read out, but the main thing is it gives us a chance to play this rather cool video. The particular point being illustrated here is that for this type of analysis, the SPH particles representing the water spray all over the place, and it's more efficient to redistribute them between the different MPP processes at certain time intervals during the calculation to try to keep the near neighbours together. And the point here is that the mortar contact is also working with that redistribution between the processes. Stamping is the next subject area we're going to talk about. Draw beads force the workpiece to move around some very tight radii, and you don't normally want to model that explicitly. So there was already a feature that modeled the draw bead as a line that applies a drag force to the workpiece, but it didn't consider the effect of all that plastic strain on the material as it was pulled through those tight radii of the draw bead. And now that effect can be modeled too, so the material will be weakened after passing through the draw bead. Next we have a few miscellaneous enhancements. Before explaining the next new feature, I first need to show what the new feature is replacing. You may be familiar with MAT24 strain rate sensitivity defined by a table. So the define table keyword gives a list of the curves of stress versus strain, together with the strain rate at which each one applies. And that's a two-dimensional table. But some material models can have yield stress being a function of more than just plastic strain and strain rate. For example, temperature may be involved. So the format for inputting this in R12 is define table 3D, which gives a list of temperatures, and each one references a 2D table, which is one of these, and each one of these in turn references the curves. And you can have more than that. You could have a 4-dimensional table which references 3-dimensional tables, which reference 2-dimensional tables, which reference curves. So it's rather complicated, and you can see why a change was wanted. So in R13, there's define table compact as an alternative to all those curves, 2D tables and 3D tables. It actually looks like a table in the keyword file. It's simple and clear to understand because it's just one keyword with one block of data, and it doesn't have this long chain of one keyword referring to another. So far, this new format is available in certain material models, and one thing to note, you do have to know what order to put the columns in. For example, the value that's being output, which here is the yield stress, has to go in the first column. While we're on this subject, it's worth pointing out that MAT24 does have an option for using a 3D table, where the additional variable is a history variable carried over from a previous stage, such as a forming analysis, via the initial stress shell card. You could even hijack this process and use a script to write your own values into the initial stress shell card, and thereby control the yield stress as a function of whatever you want, such as XYZ coordinates. And if you're trying to track down where the internal energy is being spent in a certain part, you've now got an option to split the output energy into elastic, plastic, and damage, which is supported for the list of material models shown on the screen. There's a feature for modelling resistance spot welding, where the temperature history of a central ellipsoid region is defined, and then the thermal analysis works out the temperature histories in the surrounding region, and that will all become the heat affected zone. The idea is to couple this with material models that change their structural properties according to previous temperature history. This feature has been enhanced in R13 to enable you to prescribe the temperature in the final stages of the heating via a load curve. In battery modelling, the BATMAC capability has some new features for modelling penetration by objects such as nails. Firstly, the BATMAC elements erode when the strain reaches a certain limit, and secondly, the nail can form a short circuit between the conductors. There are also some new algorithms for modelling thermal runaway, which are more realistic. And now on to XFEM. There are a number of improvements here. One is the ability to propagate cracks through T-junctions in the mesh. In terms of the initiation of failure, there's now an option for a triaxiality-based criterion, which gives a more realistic crack path. It's also possible to use the gizmo failure models in mat-add-erosion instead of specifying the failure directly on the XFEM card. Again, selection of a suitable failure model involving triaxiality leads to better prediction of the crack path. In R12, the only failure models for XFEM were based on principal stress or plastic strain, which don't predict these diagonal crack paths. The next subject is cosimulation, which means two analyses running and talking to each other as they go. The ability to co-simulate using the functional mockup interface standard was introduced at R12. In last year's presentation, some examples were shown with LS-DYNA co-simulating with MATLAB, essentially using MATLAB as a controller to apply forces to the LS-DYNA model in response to displacements. The FMU shown on the slide stands for Functional Mockup Unit, which is a model-specific thing, and it's generated by LS-DYNA. So any program or scripting language that supports the FMU standard can work with this. For instance, there's an FMU Python library. This opens up the possibility for linking LS-DYNA with other software, which might not have an FMU support, but does have a Python interface. I find that a pretty exciting idea, and I've been playing with it myself. It works pretty well. In R13, this has been extended to LS-DYNA co-simulating with another LS-DYNA analyses. So these are two completely separate analyses running concurrently and talking to each other. It's used in this example for a multi-scale analysis where one model has the big scale structure and the other contains only finely detailed models of the connections running at a much smaller time step. In previous releases, you could have done this in a single analysis with subcycling, but this method is kind of cleaner because you can build and debug each model separately before running them together. And you could also run each model on different numbers of CPUs and so on. And there's no risk of any subcycling induced issues. By the way, I'm going to test you on the details of this flowchart later, so I hope you've been paying attention to it. And there's a similar thing here for a specialist electronics application analyzing the drop test of a circuit board with all the detailed blobs of solder in a separate model. Moving on to mesh-free methods now. SPG, smoothed particle Galerkin, is very similar to SPH. Spheres are discrete points that use the same material models as solid elements to interact with their neighbors. SPG has some particularly attractive features that make it worth a look if you have situations where you'd think of using a solid element mesh, but the deformations are too extreme. Here's an application of SPG to model metal cutting. So you start from a solid element mesh, and that gets converted automatically to the SPG particles. This slide illustrates a two-stage process. In the first analysis, a self-piercing rivet is installed to join two sheets. A new feature then enables the residual stresses and deformation to be transferred to a second analysis, modeling tension and shear tests on the joint. Here's another two-stage process that's modeled with SPG. In the first stage, an anchor is drilled into a concrete block. The deformations and stresses are then carried across to a second stage where we try and pull the anchor out. Now you need a mesh-free approach in these examples because the material, here the concrete, starts as continuous, but it gets separated by the cutting process, and you can't just erode elements because that would leave a cavity which wouldn't be there in reality. SPG is very good at behaving like a liquid. It has a Navier-Stokes solver and it can model surface tension and wall adhesion forces. Here we're modeling a drop of solder. There are some improvements for discrete elements. You can now ask for a mix of different particle sizes to be injected, and the injection rate and direction can be controlled via load curves. And these new features are requested on the Define DE injection card. Moving on to ALE. Structured ALE is a version of ALE where you're limited to a rectilinear mesh, but the trade-off is a quicker solution time. This has been another area for development recently. It now has a simpler fluid structure interaction model with fewer inputs for the user to worry about, and more embedding of best practice within the defaults, which leads to fewer issues with spurious leakage through the structure. Here's an example of that. Old version on the left, new version on the right, and we no longer see the blue fluid leaking out. Friction can be added to the surfaces, and you can specify a table giving friction values on a per part basis. Now you don't want to waste CPU calculating a huge ALE domain when the structure isn't in that domain for very long, so it's most efficient to let the ALE domain change size and shape to follow the moving mesh. This was previously available only for the non-structured ALE, but has now been added to the structured one as well. The results from a region of an ALE analysis can now be captured and mapped onto a tetrahedral Lagrangian mesh for subsequent further analysis where the fluid isn't required. For example, modeling explosively formed projectiles. Once the projectile is formed and away from the explosive gases that shaped it, it's only really the speed and shape that matter, and you can carry on much more efficiently without the fluid, so then you just do a Lagrangian simulation for the next stage. And this method could also be used for castings, for example. Moving on to NVH, acoustics and fatigue. There are some new material models that you might use around the boundary of an acoustic cavity, representing trim and so on. Steady-state dynamics, which would be used, for example, to evaluate forced response functions, has become somewhat more efficient with a subcase capability so that some of the overheads of processing the model can be shared between the subcases instead of repeated each time. The fatigue solver can now use modal superposition to solve the dynamics, so it's no longer limited to a transient load case, and that makes it faster in a lot of cases. The random vibration fatigue capability now supports IGA elements. LS-DYNA does a modal analysis with the IGA elements, and these stresses are mapped onto fake finite elements which do the fatigue calculation. The acoustic spectral element method is now available, and this is intended to solve wave propagation problems more efficiently and accurately by using higher order elements, and it's applicable primarily to acoustics. So driverless cars is a big area of research at the moment, and here we see the acoustic spectral elements being applied to model ultrasonic sensors, which are used in detection of objects for automatic driving. So they're modeling wave transmission through a mesh, almost like a ray tracing approach. So the sources input a pulse, and then the model predicts what response the sensors will detect according to the shapes of the objects that are bouncing the waves back. And there are applications also in medical imaging. And again, it's a case of predicting what the sensors will pick up if waves are fired in from different points onto different shaped objects. Next up, electromagnetics. Quite a major new addition for the EM solver is permanent magnets. This opens up a whole new set of applications for LS-DYNA. Shown here are two models where opposite-poled magnets attract and snap together. And because of the way the LS-DYNA solver works, there's no need to model the air at all. It's only the magnets themselves and the things they're attached to that have to be modeled. Applications for models with permanent magnets in would include electromagnetic braking, motors, and so on. And of course, the forces from the magnets can cause motion and stresses using the structural solver. They can cause heating as well, so you've got the thermal solver to deal with that as well, and they can all be coupled together. Here's some work aiming towards patient-specific heart models. So the heart muscles are modeled as muscle fibers and the electrical impulses that feed into them that cause the muscles to contract. So with these models, we'd feed in the electrical stimuli and see how the heart beats. And then, by defining the muscle properties in different ways, we can find the effect of that. This slide shows a bit more detail of the heart models in question. It's important for patient-specific studies to try and make these models as realistic as possible, so there's a lot of work going on now in that area. And the last subject I'm going to cover today is the ICFD incompressible flow solver. The meshing library used in ICFD has now been updated. The newer version brings faster and more robust meshing, better element quality, and several improvements in other areas. And there are some new capabilities for setting up rotating meshes also. The free surface modelling has been much improved in R13 with greater stability and accuracy. This has been a big area for customer requests recently. In this example of sloshing water in a tank, we see the animation on the right here. On the left are a couple of still photos from different times in the experiment, and you can see the free surface
shape at those times. In the middle here is the R12 simulation, and on the right the R13 simulation at those same times. And you'll see there's a much better fidelity of capturing the shape of the wave in R13. In this example, the small red object is a car hood strapped to a frame, being dipped into a rather attractive purple shade of paint. The model can now simulate this use case robustly and predict the drag forces on the hood as it passes from air into the fluid, as well as while it's submerged in the fluid. So multi-species transport has been added. That means other substances being carried along with the fluid. So the initial application driving this is quite a surprising one. It's another medical application, and it's fluid structure simulations of intradermic injections, so like your COVID jab. So they've been adding a transport model coupled with fluid structure interaction. The fluid's got to flow through porous media inside the body. There's heat transfer. There's even chemical reactions and all sorts of things going on. Now, having this multi-species transport is actually going to have wider applications, I think, beyond the medical world. For example, pollutant dispersal in water systems, lakes, rivers, and even through the soil. Well, that's the end of the presentation today. So thanks everyone for listening, and see you soon. Bye.